In this next video then, we're also going to look at derivatives in a graphical way. And we're going to start with problems 109, 110, where we're given some information, some points of a function, and the values of the derivative for that function on certain intervals. And we're going to reconstruct what that original function might have looked like. So with the first one, not 109, we want to sketch the graph of a differentiable function. That just means it's going to be continuous and smooth, such that f of 2 is equal to 0. So when x is equal to 2, y will be equal to 0. We have that point there. Furthermore, we know that the derivative is less than 0 from negative infinity to positive 2, up to that point. What does it mean for the derivative to be negative in this case? And what does the derivative being negative tell us about the original function? Well, we do know that when a function is increasing, its slopes will be positive, like the examples of the red tangent segments on the blue curve there. We also know that when the function is decreasing from left to right, its slopes will be negative, as you can see from the red tangent segments on the green curve below. So if the first derivative is negative, that tells us that the function is decreasing up to that point. All the slopes on the curve must be negative up to x equals 2. And so I just draw a curve in there for which all of its slopes from negative infinity to 2 will be negative. And then we want its slopes to be positive after 2. And so we draw another smooth curve, since it's differentiable, where all of the slopes have to be positive from that point on. And that's all it takes for 109. For problem 110, we want to sketch the graph of a differentiable function f such that f is positive and f prime is negative for all real numbers. So what might that look like? If f is positive, that means the whole function has to be above the x-axis. Second of all, if the derivative is negative, means that everywhere the slopes have to be negative. And so an example of that might be this type of a curve. You can see everywhere along the curve the slopes are negative, but nowhere does the curve cross the x-axis. Then in problems 111 and 12, the graphs of f, f prime, and f prime prime, we have the function, the first and the second derivative shown on the same sets of coordinate axes. Identify each graph and explain your reasoning. Well, one thing that you want to think about is, especially with polynomial functions, is that when you start with x cubed and you take the derivative of x cubed, you're going to get 3x squared. You're going to go from a cubic function to a square function. You take the next derivative, you're going to be going to a linear function. So with polynomial functions, we can see this clear progression from cubic to quadratic to linear. And so in 111, the cubic function, or what looks like a cubic function there, is going to be the original function, and then the quadratic will be the first derivative, and the linear would be the second derivative. Now we're going to learn some more sophisticated ways of determining these things, and we won't always be working with polynomial functions, but these are clear cases of polynomial functions. So that's the first thing we want to look for. We have cubic to quadratic to linear. We went from x to the third, or some function, some cubic function, to a quadratic function to a linear function. In 112, we don't have the highest power order function we have is a quadratic, and that's the parabola shape. Then its derivative would be linear, and you should remember that the derivative of a linear function is a constant function. And so we go from quadratic to linear to constant. Again, we can see the graphs of f, f prime, and f prime prime together, and we can distinguish which one is which based on that type of reasoning. And that'll do it for this video.